Welcome to Academic Game Tutorials. In today's class we are going to study pouring, cleaning and heat treatment in foundry practice. We are studying fundamentals of metal casting and metals for casting. We will cover all related topics one by one. Before starting, if you haven't subscribed to this channel yet, just click on subscribe and press the bell icon. Here, we come up with new videos on different subjects to make the academic studies easier for you. So, into the topic. Moving the molten metal from the melting furnace to the mold is usually done using ladles. These ladles receive the metal from the furnace and allow for convenient pouring into the molds. In this figure, we can see two types of ladles. The figure A shows crane ladle, and the figure B shows two-man ladle. After the casting has solidified and been removed from the mold, a number of additional steps are usually required. Trimming, removing the core, surface cleaning, inspection, repair, if required, and heat treatment. The steps 1, 2, 5 are referred to as cleaning. Trimming involves removal of sprues, runners, risers, parting line flash, fins, chaplets, and any other excess metal from the cast part. Core removal. If cores have been used to cast the part, they must be removed. Surface cleaning involves removal of sand from the surface of the casting and otherwise enhancing the appearance of the surface, for example using sandblasting. Inspection, to detect the presence of defects, and repairing the castings if possible. Heat treatment, often done to enhance the properties of the castings, either for subsequent processing operations such as machining or to bring out the desired properties for application of the part. So, we have studied pouring, cleaning and heat treatment in foundry practice. Thank you. Icon. Here, we come up with new videos on different subjects to make the academic studies easier for you. So, into the topic. Solidification of metals. Solidification is the transformation of the molten metal back into the solid state. But, it differs depending on composition and purity. Pure metals freeze at a constant temperature while alloys, except for the eutectic compositions, freeze over a temperature range. Fluidity of pure metals are better than that of alloys. When solidification occurs over a temperature range, the partially solidified portion interferes with the flow of the liquid portion, hence reducing fluidity. 1. Solidification of pure metals. The process occurs at constant temperature over time. Local solidification time, the time over which actual freezing occurs. Total solidification time, the time taken between pouring and solidification. This figure shows the cooling curve for the pure metal during casting. Here, we can see the total solidification time is the time from the pouring temperature till the freezing is completed. And, the local solidification time is the time from when the freezing begins till the freezing is completed. During local solidification time, the metal's latent heat of fusion is released into the surrounding mold. Because of the chilling action of the mold wall, a thin skin of solid metal is initially formed at the interface immediately after pouring. Skin thickness increases to form a shell around the molten metal as solidification progresses inward toward the center of the cavity. Rate of freezing depends on heat transfer into mold, as well as the thermal properties of the metal. The metal which forms the initial skin has been rapidly cooled by the extraction of heat through the mold wall. This causes the grains in the skin to be fine, equiaxed, and randomly oriented. Further grain formation and growth occurs in a direction away from the heat transfer. The grains grow inwardly as needles of solid metal since the heat transfer is through skin and mold wall, slower cooling rate. This type of grain growth is referred to as dendritic growth. In this figure, we can see characteristic grain structure in a casting of a pure metal, showing randomly oriented grains of small size near the mold wall, and large columnar grains oriented toward the center of the casting. 2. The solidification of most alloys. The process occurs over a temperature range. As temperature drops, freezing begins at the temperature indicated by the liquidus, and completed when the solidus is reached. The start of freezing is similar to that in pure metals, thin skin and dendritic structure. The figure A shows phase diagram for a copper-nickel alloy system, and the figure B shows associated cooling curve for a 50% nickel 50% copper composition during casting. The mushy zone is a solid liquid region that has a soft consistency. The slower the heat transfer and the wider the difference between liquidus and solidus, the broader the mushy zone. The liquid islands in the dendritic matrix solidify gradually as the temperature of the casting drops. The dendritic structure favors the metal with the highest melting point. In other words, there would become a composition imbalance between the metal that has solidified and the remaining molten metal, variations in chemical composition throughout the casting. This leads to segregation of elements in the casting, called ingot segregation. Assuming a nickel alloy, we obtain a grain structure as this figure, where the comparatively lighter area shows copper-rich and nickel-poor regions, and the comparatively darker area shows nickel-rich and copper-poor regions. This figure shows the characteristic grain structure in an alloy casting, showing segregation of alloying components in center of casting. 3. The solidification of eutectic alloys. In these alloys, the solidus and liquidus are at the same temperature. Hence, the process occurs at constant temperature over time. For example, the eutectic composition in phase C equilibrium phase diagram. In the eutectic reaction, a liquid transforms into two solids. Here, in the eutectic reaction, liquid is transformed into austenite, which is represented by gamma, and cementite represented by Fe3C. In iron-carbon system, iron, 4.3 weight percentage carbon, is the eutectic composition. 1147 degrees Celsius is the eutectic temperature. Whether the casting is pure metal or alloy, solidification takes time. The total solidification time is the time required for casting to solidify after pouring, ensured TST. The total solidification time depends on size and shape of casting by relationship known as Voronov's rule. TST equals to Cm into V divided by A whole to the power n, where TST is the total solidification time, expressed in minutes. V is the volume of the casting, cubic centimeters. A is the surface area of the casting, square centimeters. N is an exponent usually equal to 2. And Cm is the mold constant, minute per square centimeter. Voronov's rule indicates that the higher the volume to surface ration, the more slowly the casting will solidify. In the riser design, it is made so that the volume to surface ratio is higher than that of the casting. That's why the riser solidifies after the main casting. So, we have discussed in details about solidification of metals, under the topic solidification and cooling. Thank you. Bell icon. Here, we come up with new videos on different subjects, to make the academic studies easier for you. So, into the topic. Directional solidification. In order to minimize the damaging effects of shrinkage, it is desirable for the regions of the casting most distant from the liquid metal supply to freeze first and for solidification to progress from these remote regions toward the riser. In this way, the molten metal will continually be available from the risers to prevent shrinkage voids during freezing. The term directional solidification is used to describe this aspect of the freezing process and the methods by which it is controlled. The directional solidification is achieved by observing Voronov's rule in the design of the casting itself, its orientation within the mold, and the design of the riser system that feeds it. For example, by locating sections of the casting with lower V by A ratios away from the riser, freezing will occur first in these regions and the supply of liquid metal for the rest of the casting will remain open until the bulkier sections solidify. The directional solidification may also be achieved by the use of chills, internal or external heat sinks that cause rapid freezing in certain regions of the casting. Internal chills are small metal parts placed inside the cavity before pouring so that molten metal will solidify first around these parts. External chills are metal inserts in the walls of the mold cavity that can remove heat from the molten metal more rapidly than the surrounding sand in order to promote solidification. The figure A shows external chill to encourage rapid freezing of the molten metal in a thin section of the casting, and the figure B shows the likely result if the external chill were not used. Riser design. Riser is used in sand casting to feed liquid metal to the casting during freezing to compensate for solidification shrinkage. The riser must remain molten until after the casting solidifies. Voronoff's rule is used to compute the size of the riser that satisfies this requirement. As the riser is not a part of the casting, it will be separated from the cast part after casting is finished. Hence, it is desirable for the volume of metal in the riser to be minimum. Risers can be designed in various forms. Side riser is attached to the side of the casting by means of a small channel. Top riser is connected to the top surface of the casting. Risers can be open or blind. Open riser is exposed to the outside at the top surface of the cope. It is disadvantageous as heat will escape faster. Blind riser is entirely closed within the mold. So, we have discussed in details about directional solidification and riser design under the topic solidification and cooling. Thank you.